Hello, my name is Junho. Today, I'd like to introduce our work, Normal Field Learning for 6GOF Grasping of Transparent Objects, or in short, NFL. The sensors for typical visual observation do not provide reliable measurements for transparent objects, especially for RGB-D cameras. Rays shot from the sensor penetrate transparent objects, resulting in wrong measurements. We can see the effects comparing the images from opaque objects and transparent objects. Thus, we need a method to reconstruct 3D geometry without depth information. One method of reconstructing 3D from multiview images is neural radiance fields, or NeRF. Using multiview consistency, where the same point in space has the same color in images, NeRF can create a volume of the object. One point to be careful of is the problem transparency introduces to NeRF. Due to transparency, NeRF suffers from broken multiview consistency. Since the background is visible through the object's surface, NeRF cannot accurately reconstruct the object's geometry. To circumvent this problem, we propose to use surface normals instead of RGB images. Using a pre-trained network, we predict and replace RGB with surface normals. This fixes the problem of background visibility and thus helps NeRF reconstruct accurate geometry. To use NeRF to build a volume, we mount a RealSense camera on our robot gripper. This way, we have access to the images and its camera parameters. Another characteristic of our work is that we build on a feature grid representation. We build on DVGo, which assigns a latent feature vector per voxel grid while using a relatively shallow MLP to regress for the color value, making the entire training process faster. We take another step by removing the MLP altogether and directly storing the normal values in the feature grid. This avoids costly volume rendering, which involves sampling and integrating along the ray direction for each pixel in the training images. So here is a high-level overview of the pipeline. We have a multi-view RGB images with camera parameters. We train a volume with estimated normal, which we refer to as normal field. Here is an example of the estimated geometry colored with normal values. The normal field provides a good enough geometric estimation that we can create a 3D trajectory of a grasp. Then we transfer the estimated trajectory to the robot and grasp the object using the trajectory. Then now let's take a look at the technical details for individual steps. Recall that the first step predicts normal from individual images. Because there is some uncertainty in the estimation, we use multiple normal estimations instead of using a single value. Specifically, we augment the input image with color transformation and predict normals for each image. We then fit a von Mises distribution for each pixel. The parameter kappa can be used as a pixel-wise uncertainty of the estimation. Additionally, we also estimate masks of the objects. For masks, we directly predict the Bernoulli parameters for each pixel. Then we combine the mask, normal, and uncertainty images from multiple views to train a neural volume. We modify the original loss function of NeRF to embrace the uncertainty in estimation. Basically, we minimize the negative log likelihood of the resulting normal considering the uncertainty. That is, we assign higher weights in the loss value for rays with lower uncertainty. Another important point is that we calculate loss only on occupied rays or where the binary mask is 1. The loss for the pixel is multiplied by the current mask estimate of B, which is 1 when there is an object and 0 when there is no object. The second term imposes a loss on the density value and minimizes the density when B is close to 0. The normal field is built on DVGo, which is a voxel-based acceleration of the original NeRF. Our voxel grid is deliberately designed to reflect the physical state. We store the implicit normal vector and density values at the 3D grid points of DVGo and directly use the stored value. This avoids costly volume rendering, which involves sampling and integrating along the ray direction for each pixel in the training images. Compared to other works that require rendering depth images, our pipeline is faster and takes about 40 seconds to capture the geometry in real-world situations. Also, our work can generalize to various scenes with the power of the strong and stable vision module trained with large volumes of real data. The figure on the right shows the voxel grid readings, SDFs from GraphNerf, and the rendered depth map of DexNerf. GraphNerf succeeds to capture the ground, but occasionally fails to reconstruct the object geometry. Jacksnerf showed good performance in the original paper, but failed in some of the images that we took. We suspect this might be due to the lack of evidence in RGB images depending on the imaging condition. The left image is what we used and it lacks strong shading cues. In such scenarios, Dexnerf fails to recover the scene geometry. After we obtain geometric estimates, we generate collision-free grasp. We do not use anything fancy, but found the grasp position using simple heuristic on contact points and normals. Also, we adapted the existing planning library in PyBullet to plan the trajectory. Our method showed the most stable grasping results. GraspNerf, although faster, did not record high success rates. More information on settings can be found in our paper. The following are some demonstrations in our environment. From images, we train the normal field and get the grasp, and actuate the grasp on a robot. In conclusion, we propose a method to get the geometry and grasp transparent objects. We do so by aggregating network outputs collected from various views in a NeRF-like manner. In addition, our grid-based representation allows fast training and grasping without any rendering process. Thank you for your attention.